So thanks for having me. So as it has been said, today I'm going to talk about some DOMPurify bypasses. So it's an HTML sanitizer. And we are going to mainly focus on default configuration, which involve some very interesting HTML parsing behaviors. So first, let me introduce myself quickly. So my name is Kévin Gervot. I'm working in a French company called Be Secure, in which I work as a pen tester. And on my free time, I'm doing mostly bug bounty, some web searches, and I play CTF with mainly two teams. I'm also making articles on my website, which should be available on the boards, on which I mostly make articles about web CTF write-ups and web researches. So before we go deeper into the technical details of all the DOMPurify bypasses that we need to see today, we need to cover some very important definition and concepts that we are going to use all along this presentation. So first, what is a client-side HTML sanitizer? Well, most of the time, it is related to a library which aims to provide to a web developer a way to make sure that there is no dangerous element into an HTML string, like scripts. So what makes a client-side HTML sanitizer more interesting to be used rather than a server-side one? It's mostly due to the fact that when you use it on the client side, you are going to use the browser HTML parser. So you have like less chance to have any kind of confusion. So as an example, here is an highly simplified version of the DOMPurify logic. So you can see on the left that it takes as an input an HTML string. And the very first thing that it's going to do is pass it as HTML. As a result, it's going to have a node tree, which contains all the HTML elements into it. And it's going to iterate on all of them and make sure that none of them contain any dangerous node name, like scripts, or any dangerous attributes, like unload. And when everything is going to be good, it's going to serialize it back to a string and returns it to the developer. So at this time, the developer is going to use it and insert it into the DOM, which will lead to a second HTML parsing. So if there is only one thing that you need to remind here, is that when you are using an HTML sanitizer, most of the time, there is going to have two HTML parsing. And that's really important. So at the beginning of the presentation, I said that if you are using a client-side HTML sanitizer, you have like less chance to have any kind of confusion because you are using the HTML parser of the browser twice in a row. So how could, in such a situation, mutation XSS even be possible? Well, if we take a look into the HTML specification, we can see that it is possible that the output of this algorithm, if parsed with an HTML parser, will not return the original string structure. So what does it mean? If we take the following string on the left and we try to parse it twice, we can see that on the first parsing, which is what the sanitizer is going to see, we have a form which contains a div which contains a form. And on the second parsing, which you can see that this time we only have a form which contains a div. And this is what the DOM is going to receive. So we have some kind of a confusion, which is due to the fact that when you are parsing HTML, it is possible on the output of the first parsing to have something which is supposed to be invalid. So here, we shouldn't have like two nested forms. And because of that, if you parse the string one more time, the invalid setup is going to be fixed, which creates a mutation when reparsing it. So something else which is commonly used when you want to play with HTML mutation is related to namespaces. So there are three kinds of them. On the left, you can find the HTML namespace. On the middle, the HVG namespace. And on the right, the MathML namespace, which all have their own parsing rules. Meaning that if you take, for example, the style tag on the left, and you try to parse it on each namespace, we can see that within the HTML namespace, the content is going to be text, while within the HVG and MathML namespace, the content is going to be null. Additionally to this, there is the integration points. So there are two kinds of them. you don't need to remind everything that is writing on the right, but you only need to see that there is the HTML text integration point and the HTML integration point, which aims to provide a way to switch from the HVG or HTML namespace back to the HTML one. So you have an example on the left. We can see that within the HVG namespace, we are using the title tag, which is an HTML integration point, which allows to switch into the HTML namespace. So this is mainly thanks to this that a lot of HTML sanitizer has been bypassed in the past. Here you can find an example of the DOMPurify 2.0.0 bypass, which has been found by SecurityMB. So we aren't going to cover this one, but the only thing that you need to see is that having the string on the top left, using DOMPurify on this version to sanitize it, we can see that what DOMPurify is seeing is a style tag which is parsed as HVG. And if you take the output of it, because of the p tag, the style tag falls into the HTML namespace. So now the content is parsed as text, which creates a confusion. And in that case, specifically, it creates an XSS. So now that we have all the information we need, we are going to begin with the first bypass, which has been found by ISysFont on version 3.1.0. So, excuse me. So this bypass involves a lot of very interesting stuff about the HTML parsing, and we are going to begin with one of them, which is the not flattening. So in the HTML specification, it is written that the algorithm described below places no limits on the depth of the DOM tree generated. Meaning that if you take like two different HTML parsers, they might be handling the limits of depth of the tree differently. As an example, here, if we take a look, for instance, at the ceiling wage, we can see that the libxml2 library, which is, by the way, used also by PHP, Ruby, and many more languages, the nested node limit is set to 255, and all the nodes above are getting removed. While in the context of the JavaScript, Python, and Java language, this time there is like no limits related to it. And finally, in the context of the browser, so here it is written that it is related to the DOM parser API, but it mainly occurs in all kind of HTML parsing that you can have in the context of a browser. So this time, the nested node limit is set to 511, and this time, all the nodes above are getting flattened. So what the not flattening is, if we take a look at the following example, we can see on the left that we have 509 divs, which contain an HVG tag, which contain a style tag. And in the output, there is like no mutation. We have the output which we was expecting to have. But if we append only one more div, this time, we can see that the style tag at the bottom is getting flattened out the HVG tag. And what is even more interesting here is that even if the style tag is getting flattened out the HVG tag, it is still parsed as HVG, meaning that the not flattening occurs after the node has been parsed. So why is this interesting? If we take again the following example, we can see on the left that in the HTML namespace, we can't have two nested A tag. But if we try to use the not flattening to force an A tag to be flattened out of an SVG tag, because the second A tag is parsed as SVG, it is possible after the first parsing to create something which is supposed to be invalid, but which is going to mutate if we reparse it. So based on that, you might be thinking that this is enough to bypass DOMPurify. But unfortunately, because of some SecurityMB research, there is a lot of mitigation in place that limit the way nodes can like switch namespaces. So we aren't going to cover it today, but keep in mind that this wasn't enough. So what ISysFont used then is related to HTML parsing state. So there is a lot of stuff about it in to the HTML specification, but we are going to focus on only two of them, which is the insertion mode and the stack of open elements. So again, in the HTML specification, it is written that the HTML insertion modes affects how tokens are processed. So tokens can also be called nodes. So in other words, it's a bit like namespaces, as we've seen at the beginning, but in the context of the HTML namespace itself. Meaning that the insertion modes aim to describe how those child of a specific node in the HTML namespace are going to be parsed. As an example, here you have the definition of the in-caption insertion modes, and it is written that if within a caption tag, we have a start tag whose name is caption, so a caption tag in a caption tag, then the HTML parser needs to pop elements from the stack. So it might not be clear here, but if we continue reading, we can see that the stack of open elements is a stack which grows downwards and has on this top the first node which has been parsed, and at the bottom, the last one which has been parsed. So if we try to take all of this information and create an example out of it, we can see on the left that we have two nested captions, so for the in-caption insertion modes, and above and below the second caption, we have a div tag. And on the right, if we take a look into the DOM tree related to it, we can see that the second div tag, because of the way the stack of open elements works, is getting popped out down the tree out of the first caption tag. So what makes it even more interesting is that the stack of open elements and the insertion modes doesn't take into account the namespace of the nodes. Meaning that it is possible to have between the two captions an HVG tag, to have some tag parsed as HVG. So on the bottom, we see that there is style tag which is supposed to be parsed as HVG. But because of the insertion mode of the in-caption tag, when we parse it, we can see that it falls down in the HTML namespace, and here we have an mXSS. So this is still not enough, because this mutation occurs only on one HTML parsing. So next, what ASYS used is the fact that the in-caption insertion modes falls back into the in-body insertion modes. So again, it might not be clear, but thanks to this, it is possible to have the payload on top left. So it is a table tag which contains a caption tag, which contains a table tag, which contains a caption tag. And here, because of the presence of the table tag between the two captions, the insertion mode is getting reset in a way. So here we have a situation where we can have like two nested captions. So if we use that situation to force the last caption tag to get flattened out the last table tag using the not flattening, it is possible to create, after the first parsing, a tree which has two nested captions, so an invalid setup, which on the second parsing is going to create an XSS. So if we sum up, to bypass DOMPurify 3.1.0, on the left we can see that we have 506 divs, and in between we have a style tag at the bottom which contain the payloads, and the two nested captions and the two nested table. On the right, so this is what DOMPurify is saying, we can see that the last caption is getting flattened out of the last table tag. So here, everything is safe because the style tag is parsed as SVG. But if we take the output and we parse it using, for example, inner HTML, we can see that this time, because of the in-caption insertion modes, the style tags falls down into the HTML namespace, which create a confusion. So the content is now parsed as text, which creates an XSS. So this is all for the first bypass. Now we are going to continue on the second one, which has been found by myself, related to the version 3.1.1. So this focus, this time, is mostly due to the way that Cure53 fixed this issue. So Cure53 is the company that developed DOMPurify. So to fix the previous issue, they put it in place two main mitigations. The first one is that now, starting this version, it is not possible to have more than 252 nested nodes. So the previous bypass isn't possible. And to track the depth of a node, they use a custom depth property, which aims to get the information of the depth. You might think that they might be using like a JavaScript API to do that, but there is no such API. So basically, they just take the current node which is being sanitized, they access the parent node, they check the depth property, and they append one. And when they reach 252, they remove all the node above. And to make sure that this fix doesn't get bypassed, they put it in place some dump clobbering protection to make sure that the depth attribute isn't something else than undefined or a number. So for those who do not know what dump clobbering is, here is a small example for you. On the left, you have a div tag which has an ID set to X, a form tag with an ID set to Y, and an input tag with a name set to Z. So on the right, on what is supposed to be a JavaScript console, you can see that by accessing the X variable, we get a link to the div tag, which has the same ID value. And if we try to do the same, but this time with the y.z variable, we get a link to the input tag. So on the second example, this is mostly due to the way links are created on form tags. And thanks to this, it is possible to overwrite like any attribute of a form tag. So what can we do is that we can, within a form tag, it puts an input tag which has a name set to parent node. So if we try to access the parent node of the form tag, the result is going to now be an input tag and not a div tag because of the dump clobbering. And if we try to access this time the depth attribute, it's going to be undefined. Why? Because now the child of the form tag is a tag which is present below the tree, so it haven't been sanitized yet, meaning that the depth attribute doesn't exist. And so this is only working because, so we can't really see on the bottom, but Curve63 was accessing the parent node property using a dot notation and not the getter, meaning that it was possible to clobber it. And meaning that we can use the following payloads. So we have 200 divs, which contain a form, which contain an input with a name set to parent node. And into it, we have, again, 200 divs. And because of the depth attribute, which is going to be undefined when the form depth is going to be computed, it is possible to reset the count, which allows here to have 500 nested tags, where the limit was supposed to be 252. So if we do this bypass twice in a row, it is possible to reach the not flattening limit again. And by simply copy-pasting the second part of the IC's front bypass, we can bypass DOMPurify again. So now, for the last bypass, we are going to focus on version 3.1.2. So for this bypass, they put it in place two more stronger mitigation. The first one is that they block dump clobbering by stop using the dot parent node access, and instead they decided to use the getter. And the second mitigation is related to the SVG to HTML namespace switch. So this one is really limiting us because the second part of the IC front bypass isn't working anymore. So on the right, you have an example of it. You can see that starting DOMPurify 3.1.2, if you try to use the title tag, which is, as we've seen at the beginning, an HTML integration point, which allows to switch from SVG back to HTML. This time, because of the limitation, all the tag which was supposed to be parsed as HTML in that context are getting removed. So I said that it wasn't possible to do dump clobbering anymore, but I was lying a bit. So here is something which could be called, in a way, second-order dump clobbering. So on the top left, you have a form tag which has an ID set to X. And what's important here is that the input attribute isn't within the form tag, but below, with a form attribute set to Y and a name set to Z. So if we try to do the same thing that we have done before when we was playing with dump clubbering, we can see that accessing x.z this time lead to undefined because the input tag isn't within the form tag. But thanks to the form attributes, if we set the form ID to the same value as the form attributes, the link is going to be recreated. So on the top right, we can see that we update the form attribute to y. And this time, if we try to access y.z, we get a link to the input tag. And why is this interesting? Well, it's mostly due to the way that DOMPurify attribute sanitizing works. So the first thing it is going to do is to take the attribute value. The second thing is to trim it. Third, to sanitize it, and then to overwrite it. So on the right, you can see that there is a small normalization. All the space at the beginning and at the end are getting removed. And the fun fact is that this occurs after the dump clubbering checks have been made, meaning that we can have something which is not clubbered when the checks are made, but clubbered after. So if we use this trick to have a form with an ID set to A with a space, and within it 500 divs, with at the very bottom an input tag which has a form attribute set to A and a name attribute set to depth. Thanks to this, it is possible to break the count again and to have something which bypass the limit. So again, at this time, we might think that this is cool and it should be enough to bypass DOMPurify again, but as we've seen, the second mitigation blocks the second part of the bypass. So this time I decided to stop reading the HTML specification and start to do a bit of fuzzing. So we aren't going to cover the script I was using, but you can simply imagine a JavaScript file with like three for loops iterating over all the HTML elements and just praying to have like something cool in the output. And thanks to this, I managed to find the following mutation, which I decided to call the elevator. You will know why in a few minutes. So on the left, you can see that there is an X tag, which contains a Y tag, which contains a Z tag, and two nested buttons, which has in between a Z tag. So what's important is also to see that there is a style tag, which is before at the same level as the first button tag. But if we parse it, we can see that the style tag falls at the same level as the tag which was in between the two buttons and above the two buttons. So here, the Z tag. So if we try to update this tag to put an X instead, we can see that this time the style tag falls at the same level of the X tag. So we have, in a way, a mutation which allows you to decide where a tag is going to fall. And using it, we also can traverse namespace. So here you can see that on the top we have a Y tag in the HVG namespace, a Z tag in the HTML namespace, and between the two buttons, the Y and the Z tag. And if we try to parse it, the style tag, which was at the bottom at the same level of the, which was at the bottom of the payload, which was at the same level of the first button tag, we can see that he falls into the HTML namespace. So the only limitation of it is that you need to have an Y tag, which is allowed on both the HTML namespace and the HVG namespace. And if we take a look into the DOMPurify source code, we can see that there is, for example, the A tag, which match exactly what we are looking for. But again, this is not enough because we can't switch from HVG to HTML. So again, I decided to do some fuzzing. And I found a variant of this mutation, which seems to work in the context of the image tag conversion to EMG by the browser. So for those who do not know, the image tag and the EMG tag are both the same. The only difference is that one is supposed to be used in the HVG namespace for the image tag, and the other is supposed to be used in the HTML namespace for the EMG tag. So here we can see that if we put an image tag in the HTML namespace, when it will be converted in EMG, the same mutation occurs, and we have the style tag which falls from the HVG namespace to the HTML namespace. So why is this interesting? I said at the beginning that DOMPurify no blocks any HVG to HTML namespace, but it doesn't blocks an HVG to HVG namespace switch. Meaning that we can use the title tag to switch to HVG with an HVG tag, and within the last HVG tag, we put the image tag. So now, by using the not flattening one more time, it is possible to force the last image tag to be flattened out the HVG tag, so he falls into the HTML namespace, but because of the way the not flattening works, it will be still parsed as HVG. So here we can create, in a way, the exact scenario we are having in this slide. So if we sum up, on the top, on the left, we have a form tag with an ID set to X with a space. At the bottom, we have an input tag with a form attribute set to X with a name set to depth. So this is for the second order DOM clubbing. And in between, we have 504 divs with the elevator mutation with the toImage tag and the toHVG tag to force the mutation to occur on the second parsing. So on the right, we can see that everything is OK. The style tag at the bottom is parsed as HVG. So this is exactly what we want. And the last image tag is getting flattened out the last HVG tag. So here we have everything we need. And if we parse it one more time, because of the elevator mutation, the style tag is going to fall down into the HTML namespace. So again, the content is going to be parsed as text, which create a mutation, which create an XSS. So this was the last bypass, but before ending this presentation, I was wanting to speak very quickly about something we have found with Ashkitten and GreHack, which is related to triple HTML parsing bypass. So in the previous three DOMPurify bypass that we have seen, there is one big limitation, which is you need to have a context which parsed your HTML string, only twice. If there is, for example, the following library, which is called mermaid.js, which use two DOMPurify in a row, or simply a website which is going to first parse your HTML on the server side before sending it into the clients, then this won't work because DOMPurify is going to detect the mutation. So what we have done is that we have further bits, and we have found the following payload on the left. So again, I'm not going to explain it, but everything is going to be detailed in an article I'm going to release after this talk. The only thing that you need to see is that on the first parsing, so the DOMPurify one, the depth of nodes is going to be 4, and we have a specific pattern which is repeats 510 times. If we parse it one more time, this time the depth is going to be increased by the number of patterns, so here 510 times, which is going to trigger the not flattening. So we have some tags which was parsed as HTML, which no falls in the HTML namespace. But again, because of the way the not flattening works, there is like no mutation here for the moment. But if we parse it one more time, this time we get an XSS, as the style tag is going to be parsed as HTML. So there is a switch between text and HTML, which creates an XSS. So finally, what's next? So to fix also this issue, Cure53 decided to put in place a specific regex, which you can find on the boards. So essentially, what they was doing is they decided to stop allowing any kind of HTML comments, style tag or title tag closure within an attribute. So this is huge because this was used in any mutation XSS bypass. So I think for the moment, at least, it will be like really hard to bypass DOMPurify. So to conclude, in this presentation, we have seen 3 DOMPurify bypasses on default configuration, which involves a lot of interesting HTML behaviors, like the not flattening, the insertion modes, the elevator mutation. But something which is really important to remind is that today, the whole DOMPurify security relies only on a simple regex, meaning that there is some very specific configuration that we are going to cover today, which can lead now to bypass even on the latest version. And this is going to be the subject of an article I'm going to release in like 2 or 3 weeks. And yeah, that's all. If you have any questions, do not hesitate.